again. My name's John Carlisle. This is tutorial 1.6 in a sequence of tutorials about the preoperative cardiopulmonary exercise testing. And as you can see from the subtitle, I'll be talking about the 9-panel plot. I have italicized the because there isn't a single 9-panel plot. If you recall, at the end of 1.5, I was talking about the 9-panel plot being laid out as a sequence of squares 1, 2, 3, 4, 5, 6, and 7, 8, 9. Now, the historical purpose of the 9-panel plot was to lay out the results of a cardiopulmonary exercise test to summarize the main features, the prognostic and diagnostic features of a test. With computers, software, etc., you can interrogate a cardiopulmonary exercise test using the raw data, and you can manipulate pictures and so on yourself on the screen of a computer rather than relying upon a printed out 9-panel plot. However, it still serves the purpose that in the patient's notes it's something you can refer to, and it summarizes the patient's fitness. There are two main layouts of a 9-panel plot, bearing in mind that there are potentially thousands of different combinations of plots you could potentially put on. So there's basically two, and those plots are what's called the Wasserman plot and the Witt plot. Looking at the Wasserman plot first of all, over here, you just see I've just numbered the panels 1, 2, 3, 4, 5, 6, 7, 8, 9. If we were then to transpose those panels into the Witt plot, you'll see that they occupy different places. So panel 1 isn't present in the Witt plot. Panel 2 is in the right hand corner of the Witt plot, and so on and so forth. In the second, so that's on the first row here. In the second row, I've taken the Witt plot as the reference 9-panel plot and shown where those different squares would lie in the Wasserman alternative. You'll see that in both plots there's only one panel that exists in the same place, and that's panel 8. What I'm going to do is delete this, bring it back in and miniaturize it, and then talk about the different panels and what they are. So let's bring that back in, and this time I'll shrink it down. We'll just leave it lurking in a corner somewhere. So let's pop it over here, and then we can go through the panels as you would wish to do after a patient's completed a cardiopulmonary exercise test. And in both plots you would want to go to panel 8 first of all, and in panel 8 is that plot of the respiratory exchange ratio against time, and the main feature of that plot is to check that at the beginning the patient isn't hyperventilating, so the plotted data lie under the value of 1.0 and subsequently cross it towards the end of the bicycle test. The reason that you're doing that is you want to check that the patient is not hyperventilating. If they are, or if they were, then that means your identification of the anaerobic threshold is in question, because the removal of carbon dioxide from the carbon dioxide reservoir bound to hemoglobin and in carbonic acid and bicarbonate ions. If you've exhausted that reservoir, then when you get supplemental CO2 being generated by anaerobic respiration in the cytoplasm, that's going to form acid first of all and bicarbonates, and you may not breathe it out, so it obscures the AT. So you want to just check that the patient wasn't hyperventilating. So that's the first panel you want to look at in the 9-panel plot. The next panel you want to look at is panel 3 in the Wassermann, which is in panel position 2 in the whip. So panel 2. And that is really just a miniaturized version of your data plotted out during the bicycle ride. So oxygen consumption, carbon dioxide output, and you're doing that for a number of reasons. Often on the plot you have a predicted value. I'll be talking about predicted values in another tutorial, but you can see how close the person got to their predicted value. However, there's loads of different predicted values, but they all scatter around whichever predicted value you decided to plot out. So that's one thing. I also like, there's time along here, I also like looking at how long they've exercised for. So we've got a rest period, we've got the 3-minute period against cycling against no resistance, and then a variable period after that before the patient stops. And although we've aimed for it to be 10 minutes by programming the ramp rate, again I'll be coming to that on another tutorial, it may not be 10 minutes. So you just want to see how many data points you've got. If this is a very short period, then you may not be able to interpret what it all means. So that's the second bit you want to look at. Now the other panel in common that you would want to go to next is the panel that you primarily use to identify the anaerobic threshold. Okay, so in the Wassermann one it's in the middle, and in the whip version it's at the top of this column. We'll come to that column in a moment. So remember that we identify the anaerobic threshold by plotting carbon dioxide output against oxygen consumption. Oxygen consumption. And having done so, we get a sequence of data points. We bring in a unitary tangent from the bottom right. From the bottom right. And where it touches, we draw a vertical tangent, a vertical line down, to the horizontal axis, and we define the anaerobic threshold as where the oxygen consumption at this point. So that is panel 5. Now, at this point, the two layouts start to digress from each other. So I'm now going to concentrate on the whip version because the whip plot nicely lays out these 3 ways of identifying the anaerobic threshold in a single vertical column. So at the top we've got the plot we just discussed, so carbon dioxide output against oxygen consumption. All the lower 2 panels, well, in the whip plot there, panels 4 and 7, we have the other supplementary ways of identifying the anaerobic threshold. And hopefully you'll recall that your sort of wingman method of identifying the anaerobic threshold is going to be a plot of oxygen consumption on the horizontal axis against two plots. One is the ventilator equivalent for carbon dioxide, and the other is the ventilatory equivalent for oxygen. And you'll recall that during the bicycle ride both come down as gas exchange improves, with the ventilator equivalents for oxygen coming down to excuse me, a nadir at about the anaerobic threshold and then going up again. So these should be coincident. So I'm going to draw a vertical line down. And the final plot to support your identification of the anaerobic threshold is again another plot that's got two vertical axes. One is the carbon dioxide end-tidal partial pressure, and the other one is the oxygen end-tidal partial pressure, which again reaches a nadir at the anaerobic threshold. And you may have a secondary increase in ventilator equivalent for carbon dioxide and in partial pressure of end-tidal carbon dioxide. So that would be the respiratory compensation point, and the earlier change is coincident with the anaerobic threshold. So that's quite useful feature of the Brown-Witt plot, is 9-panel plot, is that these three useful graphs are all laid out vertically, and if the horizontal axis is to the same scale, you can then visually look up and down to check that these changes are all coincident. They often aren't quite, but they're quite a useful way of summarizing the three ways of identifying the anaerobic threshold. So where would we go to next? Well, let's get rid of this black box I've accidentally made. Well, you could go to a number of places. Often one might wish to look at in the Vosserman plot, it's panel 2, and in the Witt plot it's in effect in position 3, and that is a plot again of two variables. The thing is that you actually can't quite see on the, let's bring that in again large, you'll see that I have put in around some of these panel points a dashed black line, and that's because the axes aren't necessarily the same. So the equivalent panel in Vosserman will use a different horizontal axis compared to the Witt. So Witt 9-panel plot generally uses, not all the time, but generally uses oxygen consumption as the horizontal axis, whereas the Vosserman plots will often use either time or power. So where were we? We were going to talk about this panel here, panel 2 in the Vosserman, and position 3 in the Witt, and it is a plot of either against oxygen consumption in the Witt plot or time in the Vosserman plot. The two vertical axes are the same. One is heart rate, and the other is that ratio we call the oxygen pulse, which is oxygen consumption divided by heart rate. And you remember that as oxygen consumption increases, and as time progresses, your heart rate is going to go up on both panels, even though the horizontal axis is somewhat different. The dots go up similarly, but not precisely the same, because the horizontal axes aren't different. And the oxygen pulse forms a hyperbolic graph in both, really. And there you're looking for abnormalities in heart rate, so heart rate reserve at the end. Is the peak value matching the predicted value? And for the oxygen pulse again, do you reach the predicted value? Remember, the hyperbolic curve does resemble a horizontal line, so sort of a horizontal end to it is not abnormal. And we're going to talk about abnormal patterns from the next tutorial probably, unless I think of something else to talk about. So that's the next one you would look at. We'll get rid of that now. Oh, sorry. So we've talked about quite a few of them already. So we've talked about 1, 4, and 7, the equivalent. So 1, 4, and 7 in the WIP, which in the Wassermann one, 1, 4, and 7. I quite like white on that, don't you? So we've talked about those already. We've talked about that panel as well. We've talked about that panel there. We've talked about 8 on all of them. 9 on the... Actually, what shall we talk about next? Let's talk about panel 5. 5 in the WIP, which is panel 6 in the Wassermann, and that one is the plot of... Hang on, I'm going to do a sneaky peeky because I keep on forgetting. Wassermann, yeah, that's the one. Let's go back to where we were. So this panel here, 5, let's just double see how it's confusing having two layouts, because I'm getting confused now. Let's just check again. So I want to talk about that plot there. Actually, let's just stick where we are. So this plot is just another way of plotting out the Venti equivalent for CO2, and you're looking for abnormalities there in the slope. This plot down here, so plot number 7 in the Wassermann, in the WIP plot, that's over here in position number 6. And that's quite a nice one to look at, because that shows you the change in tidal volume with changing minute ventilation. Remember, you breathe deeply first, so values go up. And then as you run out of inspiratory capacity, so you've got a inspiratory capacity ceiling, you often don't reach it under normal circumstances. You then basically increase minute ventilation by breathing quicker. You've got as big as breaths as you can. And previously you have estimated or directly measured the maximum voluntary ventilation, and we should see a breathing reserve here of at least 15%. Okay, so that plot. Let's see if we've missed any out, shall we? Shall we go and have a little peek at that? Oh, let's leave that green for the time being. Let's go and have a little peek. This is one of the graphs we use. This is from Denny Levitt. Thanks, Denny. I didn't ask for permission to show you this, so that's why I was trying to steer away from looking at it. We've pretty much talked about everything there. So you'll see that's Fusserman, that's whip. And you'll see the use of the whip in these three graphs or panels all together. Okay, I think we are pretty much near the end. So what we've talked about in this sixth tutorial is the 9-panel plot, and the fact that there's basically two common 9-panel plots that people talk about, the whip plot and the Wassermann plot, and you'll probably get familiar with one more than the other. You may prefer the whip to check the anaerobic threshold, but as I said, in reality, what do? You don't really use, or personally, don't really use the 9-panel plot often on a piece of paper if you are in the room where the CPET is being done. So you're either one in the room, and then you're going to use the computer, although we often will print this out. Or you may work in a service where you get delivered the results of the cardiopulmonary exercise test to interpret in a lonely room with the curtains drawn, and in that case you do want to use the 9-panel plot, so you need to get familiar with both of them. Okay, let's call it quits there. Thanks for listening, and I don't know, the next tutorial is going to be a surprise because I haven't decided what it's going to be.